Hello everyone, today we're going to look at dividing radicals. So recall from rules of exponents that the square root of something divided by the square root of something is the same as the square root of the division. So division and radicals, which are a power, it doesn't matter the order in which you do it. I can square root and then divide, or I can divide and then square root. Which one I do depends on my numbers. If the two radicands, so what's inside the square roots, on, say, the left are perfect squares, then I want to square root before I divide. If what's inside the square roots are multiples of each other, or they have factors in common, then I want to divide first. Okay, so it's going to depend on what it looks like for what I want to do first. So let's simplify the following. The square root of 12 divided by the square root of 3. So if I notice, neither 12 nor 3 are perfect squares, but 12 does go into 3 evenly. So I'm going to rewrite this as the square root of 12 divided by 3, which is the square root of 4. And the square root of 4 is 2. For our second one, 25 and 49 are perfect squares, so I'm going to square root them separately. And I'm going to get 5 over 7. And I can't simplify 5/7 any further, so I'm done. For the next one, I can go one of two ways. I can look at 9 and say that's a perfect square, so I'll square root it. And then I'll look at 12 and say it's not a perfect square, but I can simplify it. Right? 12 is 4 times 3, and root 4 is 2. So I can have that root 9 over root 12 is 3 over 2 root 3. Or I can simplify 9 and 12 and say 3 goes into both of those. So if I take root 9 over 12, that becomes root 3 over 4. Right? 9 and 12 both have a 3 in common. And then I can't square root 3, but I can square root 4. So this would be the square root of 3 over 2. Notice in this guy, the square is over the whole fraction, whereas in this one, the square root is just in the numerator. So you want to be really careful when you're writing square roots and fractions, and you want it to be very clear what is actually inside the square root. So I can have either 3 over 2 root 3, or root 3 over 2, and we'll see in a little bit that those are actually the same thing. Okay, so either one is perfectly fine, and they're both correct. Let's do some more. Root 7 over root 14. So I can't simplify either one on its own, but 7 and 14 have a factor in common. So if I put them together first, I can get rid of 7 and be left with the square root of 1/2. The square root of 1/2 is the same as 1 over root 2. Since this is the same as this, and the square root of 1 is just 1. Okay, so the square root of 1/2 or 1 over the square root of 2, again, it's the same thing. For my second one, again, I could do one of two things. I could either square root both of them. They are both perfect squares. Right, root 36 is 6, root 4 is 2, and then 6 divided by 2 is 3. Or I could divide and then square root. If I divide first, 36 divided by 4 is 9, and the square root of 9 is also 3. So in either case, we're going to get 3. For the last one, notice that I have a variable too. So again, I could simplify the top and simplify the bottom separately. 18 and 27 aren't perfect squares, but they do have factors that are perfect squares. Or I could simplify the fraction first. So I'm going to do that, and I'm going to rewrite this as the square root of 18x cubed over 27. And say to myself, 18 and 27, they have a 9 in common, so I'll get rid of it. So I'm left with 2/3 x cubed inside the square root. The square root of x cubed, hopefully we can remember, is going to be x root x. right? 3 is an odd number, so I pull 1 out, I'm left with the square root of x. That's the square on the outside. The 1 that I pulled out is the one that's still inside the square root. And then I still have the 2/3 also inside the square root. So I put it together and I have x on the outside and the square root of 2x over 3 on the inside. Let's try some more. Root 45 over root 9 times y to the 4th. So again, I could square root the 9 and I could simplify the square root of 45. Or if I notice, 45 goes into 9 evenly, so I can just do the division out first. So root 45 over root 9 is root 5. And then that goes on top, and on the bottom, I still have the square root of y to the 4th, but y to the 4th is even. So when I divide 4 by 2, I'm left with y squared. So we have root 5 over y squared. For h, again, I can do it one of two ways. If I notice, 81 and 36 are both perfect squares. So if I go to square root them, I have 9 over 6. 9 and 6 both have a 3 in common, so I can leave it as 3 over 2. Or if I divide first, 81 and 36, they have a 9 in common, and if I get rid of the 9, I'm left with 9/4. And then the square root of 9 is 3, the square root of 4 is 2. So either way, I should get 3 over 2. And then we have 12 over root 32. So 12 doesn't have a square root, so I can't square root them first. I can't divide them first and then square root because there's no square root on the top. So what I'm left with is simplifying the bottom. So the top is still 12. 32 is 16 times 2. Square root of 16 is 4. So I'm left with 12 divided by 4 over root 2. 12 divided by 4 is 3. And then the root 2 is still in the bottom. Okay. And then the last couple that we're going to look at are not just dividing fractions, but what's called rationalizing the denominator. And that means getting rid of a radical that's in the denominator. So a lot of people, when they think of denominators, they think of dividing. And mentally, at least going back to, 3rd or 4th grade, when you think of dividing, you think of separating things into piles, right? If I want to take 12 divided by 4, I'm going to take 12 items and put them into 4 piles. But I don't know what root 2 piles is, right? And that's kind of hard to conceptualize. So we like our denominators to be integers whenever possible so that it makes more sense in our brains. So what we're going to do is we're going to use the fact that root a times root a is a, right? Root a times root a is root a squared. Those cancel, and we're left with just a. So root 10 times root 10 is 10. Root 12 times root 12 is 12. Root x times root x is x. Okay, so we're going to use that to turn any radicals that we have in the denominator into integers, possibly some variables. So the question is how? So I have something like 2 over root 3. I have a radical in the denominator, and I say I don't like that. I want to change that into an integer. So there are two things that I can do to a number that won't change it. One is add 0. That's not going to be helpful with fractions because I don't want to have a common denominator. The other thing I can do is multiply by 1. So the really nice thing about 1 and fractions is that I can choose any number that I want besides 0, and if I put it over itself, it's 1. So in particular, I want to choose my denominator. Not just my denominator, but the radical part of my denominator. So my whole denominator is the radical. So I'm going to write root 3 over root 3. It's a 1, so it's not changing the number, right? But it's going to help me because now root 3 times root 3 is 3. So my top is 2 root 3, my bottom is 3. So I have now rationalized the denominator. I went from a radical to an integer. So we're going to do that on some more examples. So 4 divided by 8. Before I start rationalizing, I always want to simplify. because that's going to be less simplifying later on. So 4 over root 8. Root 8 is root 4 times root 2, which is 2 root 2. So I have 4 over 2 root 2. That's a 2. I can cancel a 2, and I'm left with 2 over root 2. So before any rationalizing, I've already simplified my fraction. Now I want to rationalize it. I want to get rid of that root 2 in the denominator. So I'm going to multiply by root 2 over root 2. So on my top, I'm left with 2 root 2. On the bottom, root 2 times root 2 is 2. I can keep going, the 2's cancel, and I'm left with root 2. So 4 over root 8 is just the square root of 2. For the next one, 2 root 3 over root 15. Again, I want to simplify everything that I can first of all. So I'm going to look at root 3 over root 15 and say that they both have a 3 in common. So I'm going to cancel the really a root 3, and I'm going to be left with 2 over root 5. And then I'm going to rationalize it. And then my denominator, again, becomes a 5, and my numerator is 2 root 5. If I didn't rationalize it first, I'd be multiplying the top and bottom by root 15. So if I multiplied top and bottom by root 15, again, without simplifying first, I'd be left with 2 root 45 on top and 15 on the bottom. Then I would look at 45 and say that that is is 9 times 5. And root 9 is 3, and I still have a 5 on top. And then I look at it and say, okay, 3 goes into 15 5 times. And there is my 2 root 5 over 5. So as long as you simplify at some point, it's okay if you don't at the beginning. But I always feel it's better to simplify first because it usually involves less simplification later on. Okay. But in either case, you should be getting 2 root 5 over 5. The next one, 2 root 6 over root 7. I can't simplify that at all. 6 and 7 have nothing in common. They are not simplifiable on their own, right? There's no factor of 6 that's a square. There's no factor of 7 that's a square. So the only thing I can do here is multiply top and bottom by root 7. And if I do that, again, my bottom's going to be 7. My top will be 2 root 42. And again, 42 doesn't have any factors that's a square. My last one, 5 over root 5. Again, the only thing I can do is start to rationalize it. Right? I can't simplify root 5, and there's no square root on top to simplify further. So I'm just going to multiply by root 5 over root 5. So I have 5 root 5 on the top. I have 5 on the bottom, and those 5's cancel. So I'm left with just the square root of 5. Okay. So I want you to make sure you read through the book, try out the homework, and let me know if you have any questions. Thanks.